from here, but like Lifetime Fitness is where I get workout.
Do you have any homework questions?
Yes. Me.
So I might have one in particular.
Wow.
Oh, I didn't even see the kid.
25.
They just see it in everything.
Sorry, which ones? 17 and 20.
Wait. Are we on 3.6?
We're on 3. We started 3.7 last time. Is that it?
Let's pretend I didn't say anything.
Okay. So,
I don't know what you're talking about.
I got one.
Okay.
3.4, number 20.
Wait.
3.2.
I don't remember it then. We're just gonna put it there.
which part in particular?
For me, it was going to be part, what was it? I think it was C.
Uh-huh. So this was like the example we worked in class.
Give up on that.
What time is the instantaneous growth rate the greatest? Instantaneous growth rate is described by P prime of t. And notice the technology. So what you want to do is just graph P prime and just look for the highest point.
So it looked like it was infinity.
Well, shouldn't have been. What did you get for the derivative of P?
If I remember it, my derivative, well, on mine it was 200 over, in parentheses, 2 plus x squared. But mine was slightly different than what you guys saw.
Okay. Yeah, so that's how we would answer that question. At this point, we don't have the techniques necessary, so we do have to just graph it.
Okay.
And we did one like that in class. I don't know if we did that exactly in 3.4, but I think we did when we were talking about the quotient rule. We looked at an example like that. Any other questions? All right. So we left off, we just started 3.7. Like we mentioned last time, the chain rule is for taking the derivative of composition of two or more functions. And there was two versions presented. The first version where it's dy over du times du over dx. So that is the chain rule, just in different notation for the derivative of y with respect to x. That version involves us making a substitution where u is the inner function. And then so we compute the derivative of u, and then we compute the derivative of f of u as a variable of u. Once we make that substitution, all of our x's in that function would turn into u's. So we just take the derivative of that function with respect to u, and then with our substitution, u equals to like 2x, for instance. We take the derivative of that with respect to x, and then we multiply those two results together. Version 2 doesn't involve a substitution, but it's the same idea as version 1. We take the derivative of the outside function, f, and leave the inside function alone. Okay, so that gives us f prime g, so g is left alone there, and then we multiply by the derivative of the inner function, which is our g prime in that notation. Okay. So an example of that would be to find the derivative of 3x plus 5 to the 100th power. Now, before this, we had the product rule and power rules. So without the quotient rule, to take a derivative of something like this, you would have to multiply it out 100 times, expand all of that stuff, right? And then take the derivative of each term. Or we could say it's 3x to the 5th, 3x plus 5 times 3x plus 5, and just multiply 2 out at a time. and using the product rule, which would also take forever. So we'll look at both versions. Let's start with version 2, because I honestly think that one's ultimately is easier, but I think version 1 might give a little bit better insight as to the process of the chain rule. So version 2 says we take the derivative of the outside, leaving the inside function alone. So really, when you're looking at a composition, you have to determine, well, what would the outside function be and what would the inside function be? So what would the outer function here be? Yeah, the outer function is taking this expression and raising it to the 100. So we've got, like, you could pretend like this is something to the 100, x to the 100, and the inside function is the 3x plus 5. So we take the derivative of the composition by taking the derivative of the outer function, leaving the inner function alone. So we just apply the power rule to that. So with respect to the formula, the generic formula, this is f prime of g of x. Was everybody able to see that? Just the derivative of the outside, inside's left alone, and then we have to multiply that by the derivative of the inside function. So the derivative of 3x plus 5.
I'm sorry.
Okay. And then that portion is g prime. So I know you know the derivative of 3x plus 5, but I would write these things out. When you say the formula involves a derivative and you say derivative in your head, write that notation out. So are there any questions on that, how we come up with those two things? Now, of course, every function's different, so every inner and outer function will look different. And that's part of the difficulty, I think, with the chain rule. Okay, and then we'll simplify this. We've got our 100, 3x plus 5 to the 99, times the derivative of 3x plus 5, which is just 3. So we'll say that's 300 times 3x plus 5 to the 99. And even more beneficial too, the derivative is also in factored form too. So you could imagine you have all of these terms from the derivative that you multiply this thing out times itself 100 times, right? And then you have this giant polynomial that's to the 99th power. And then you could imagine trying to factor that. It's not an easy task at all. But this chain rule for things like this particularly keeps everything nice and compact. Are there any questions on that? Okay, then version 1, rather. We just did version 2. Version 1 has us making a substitution. Remember, version 1, it says that the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. So our y with respect to x, 3x plus 5 to the 100th, involves a substitution. The substitution was let u equal to g of x, but more operationally, we let u equal to the inside function or the inner function. So our substitution, we have to say let u equal to 3x plus 5, because because that's our inside or inner function. And when we let u equal to 3x plus 5, y becomes u to the 100th. So then y is u to the 100th. And then to take the derivative of the original function, it says we take the derivative of y, dy over du, derivative of y with respect to the variable u. In other words, this is y prime with the variable u. So what is y prime here? What's y prime?
100 to 99.
Yeah, 100 times u to the 99
Times u prime.
times,
U prime.
yeah. And then we've got this piece, dy du, is right here. So this is dy du. And then we have to multiply that by the derivative of u with respect to x. So here's u with respect to x. We take the derivative of u with respect to x. So what's the derivative of u with respect to x?
3.
3. In other words, that second piece is saying you find u prime with the variable x. So I'll just, since I'm running out of space here, u prime is equal to 3. And this one, du dx. So all we got to do is multiply those two results to get the derivative of y with respect to x. So y prime is equal to dy du, 100 times u to the 99th, times u prime, which is 3. So then you have to resubstitute because we want the derivative of y with respect to x. Right now we have the derivative, a mixture of the two things, really. So the last step here is to just resubstitute for that u. U was 3x plus 5. Which, again, we see that was the same result we had with version 1. Any questions on that? Doesn't matter which version you use. As we see, they both result in the same derivative. So whichever one seems more comfortable or makes more sense to you, please use that. Okay, how about the square root of x squared plus 1? Using version 1, we'll make a substitution. And what would u be equal to for version 1? The inside function x squared plus 1. So if u is x squared plus 1, that gives us y equals to the square root of u. And then we find the derivative of those two things, multiply those two together, and then resubstitute for u. So what's u prime? 2x. What's y prime? With respect to u.
1 over 2 the square root of u.
Yeah. So remember roots, we're thinking about that's u to the 1/2 using the power rule to find the derivative. 1 over 2 root u. So then, basically, y prime, and this is where the notation, we should be careful with our notation so it's not misleading. But that's basically what we're doing here. But when we talk about the y prime overall, we're talking about the y prime here, the derivative of this function with respect to x. So we have our 2x times this function, 1 over 2 root u, and then we just resubstitute for u. We can simplify the 2's divide out, so we have, this is x over the square root of u, and that turns in, once we resubstitute, that's x over the square root of x squared plus 1 for the derivative of y with respect to x. This is dy dx. This one up here is dy du. Yeah.
Are there certain situations where like one version works better than the other?
I don't think so. There are certain situations where one version works better than the other. And I don't really think so. I think it's just a matter of how you see it. I think maybe in practice, you would start off using version 1 until you got a sense of how version 2 works. But once you get a sense of version 2, it's honestly a lot more efficient because you don't have to substitute and resubstitute. Are there any other questions on that version? If you look at a function and you don't know what the inner function is and what the outer function is, just think about it in terms of operations. Like if I plugged a value in for x, what would I do first? In this function, I have to square it and then add 1 before I take the square root. So the squaring and the adding 1, that's our first function, or our inner function. And then we take the square root, that would be the outer function. So maybe you could think of them as like first function and last function. Okay, version 2 with y equals to the square root of x squared plus 1. We're going to think about that as x squared plus 1 to the 1/2 before we take the derivative. And second version's derivative says that we take the derivative of the outside, leaving the inside alone. So here's the derivative of the outside using the power rule. And we're going to leave the inside alone. Then we multiply by the derivative of the inside. Again, I'll reference back the formula here. This is f prime of g, and this is g prime. Are there any questions on that? Okay. And then we take the derivative of x squared plus 1. And then we divide the 2's away. So we have x times the quantity x squared plus 1 to the negative 1/2, which is the same as the result we had with version 1. Rewrite this with positive exponents and radicals. It's the same result. Yes, question?
Yeah, if we left it like the one at the top right there, would you allow that?
This one here in the middle or this one up here?
Down and then the
To the right.
answer?
Yeah, this,
Yeah, if we left it like
Yeah.
that on the test, would you?
yeah, I'm fine with that. Again, that's another hard part about grading stuff like this, is some people will leave it as negative, the exponent is negative 1/2. Some people will write it as x over x squared plus 1 to the positive 1/2, and some people will write it x over the square root of x plus 1. X squared plus 1. So, you know, honestly, any of those variations are totally fine. Any other questions? So we've seen kind of a power function. Radicals are also power functions, so they work in a similar way. Exponential function, how about e to the power of sine x? What would the inner function be here? Is what? Yeah, it's sine x, right? If you plug in a value for x, you have to compute the sine of that value first. So u is sine x, the inner function or the first function. And then what that means, if we make that substitution, that means y is equal to e to the u. So what is the derivative of u with respect to x?
Cosine x.
Derivative of sine is cosine. And then what's the derivative of y with respect to u? E to the u. Derivative of y with respect to x of e to the x is e to the x. So the derivative of the original function y prime is the product of these two derivatives here. It's e to the u times cosine x. And then we'll resubstitute for u. I'm going to do this. So our derivative is e to the sine x times cosine x. And usually you'll see that the exponential is written last just to avoid, you know, confusion or sloppiness as to what's actually the exponent. So we'll put the cosine first, so there's no issue as to where that cosine is. So as these functions change, their structure changes. So you have to be aware of what's the inner and what's the outer. Sometimes you can have a function that consists of the composition of 3 functions as opposed to 2 functions. So when those arise, you have to be more careful. Okay. So version number 2. The derivative is equal to the derivative of the inside function, or sorry, the derivative of the outer function, leaving the inner function alone. Times the derivative of the inner function. And we see that version also gives us the cosine times sine, e to the sine. And we'll label this. So that e to the sine is just f prime of g. And this is g prime. So when it's e to a power, that e to the power part as a function of x is always the outer function. So we see that's there because the derivative of e to the u, if we think about it in light of version 1, the derivative of e to the u is e to the u. So that's why this piece is still there, and then we have to multiply by the derivative of its power. Do y'all have any questions on that? It almost looks completely different than the last two we've done because it's a completely different function, but it's still the chain rule applied to that function, so it takes on a different flavor.
And this helps us find what, y prime in a different way.
Mm-hmm, right. Yeah, so if your function describing some sort of whatever population or whatever you're measuring was e to the sine x, how do you take the derivative of that? How do you find the instantaneous growth rate? So we're gonna look at a more generic definition of the derivative for e to any function of x, because this is one that's really, it's commonly missed. Okay. So our generic statement we're gonna write down is, if I take the derivative of e to any function of x as the power, when I take the derivative, the e to the f of x part stays, so it's still e to the f of x, but by the chain rule I have to multiply it by the derivative of the inner function, which is the exponent. So it's f prime of x times e to the same power. Think about it as like it's the derivative of e to a power. As long as that power is a function of x, the derivative of e to that power is e to that power times the derivative of the power. And maybe we should say here where f of x is not constant. Okay. So e to the power times the derivative of the power is how we take the derivative of e to anything except a constant. So what would the derivative of e to the 3x be?
3x times 3.
E to the 3x times 3. Do y'all agree with that?
So e to the 3x.
So there's e to the same power times the derivative of its power. Derivative of 3x is 3. So there's just, when you take the derivative of an exponential, the exponential is still going to be in your derivative as it's originally presented to you. What's the derivative of e to the negative x? Y prime is negative e to the negative x. What do y'all think? So the derivative of e to that power is still e to that power times the derivative of the power. So let's write that out. E to that power times the derivative of the power. The derivative of negative x is negative 1. So they're all, what we're looking at is just kind of e to a linear function, right? So we can generalize that and say, well, what's the derivative of e to the kx with respect to x, where k is any real number? What's y prime for this function?
K e to the kx.
Good, yep. It's k times e to the kx. 3 times e to the 3x, negative 1 times e to the negative x. this is our lockdown drill. Okay. So a couple more with e to the power. Example 4, what would the derivative of that e to the negative 0.01x be?
Negative 0.01 to the negative 0.01x.
Right, yep. The negative 0.01 is acting as that k. So our y prime, negative 0.01 times e to the same power times x. Anybody have any questions on this? So this is just, we are using the chain rule to take these derivatives. Just a different function, so it looks a little bit different. What's the derivative of e to the x squared?
2x e x squared.
Right. So back up to the derivative of e to any function is e to the function times the derivative of the function. So y prime is e to the function x squared, e to the x squared, times the derivative of x squared. So that's 2x times e to the x squared. Is everybody all right with that? Seem easy enough? Hopefully. What's the derivative of number 6?
Squared minus 2x times e to the power of 3x cubed minus x squared plus 1.
Right, yep. So we have the derivative, it's still e to that power. Times the derivative of the power. Derivative 9x squared minus 2x, that quantity, times e to the original power. So derivative of e to the third.
0.
0. How do we know?
It's a constant.
It's a constant. E cubed is a constant. We could still think of it as e to the power, the derivative is e to the power times the derivative of the power, right? But the derivative of 3 is 0, so we have e cubed times 0, which is 0. Do y'all have any questions on derivative of e? So what's the derivative of secant of e to the x? Notice this isn't e to the power, right? It's not e to the secant. It's the secant of e to the x. So what is the inside function here? E to the x, and the outer function then is secant. So what's the derivative of secant?
Secant x tangent x.
Secant tangent. So it's secant tangent. Remember that first part is where we leave the inside function alone. So this is secant of e to the x tangent of e to the x. And then what do we multiply that by? Yeah, the derivative of the inner function, which is e to the x, times the derivative of the inner function, which is e to the x. Just want to write that out so we can clearly see the rule. And so it doesn't matter where we put that derivative, e to the x, usually put up front, so we have secant of e to the x tangent e to the x times e to the x. If you're looking at that through version 1, then u is e to the x and y is secant of u. Y'all have any questions on that? Okay, so why don't you all try example number 5. It's the cosine of e to the sine x.
So there shouldn't be, sorry about that, the derivative of patterns.
Yeah, you do, but you should have negative sign of e to the sine.
Oh,
Yeah, and then the derivative of each of the derivative. The other sign.
I like to go over each. I like to still have them all. Make a little table that I can refer back.
Makes sense. If I put that.
This would be cosines. Just
Now, so it's top on first.
That's just fine.
Did you ever do that?
Yeah, just as long as it's clear to you that that's not an actual cosine.
But it's supposed to be.
No, because that's e to the derivative of that is e to the sine times the derivative of sine.
It's like a weird stage.
But it shouldn't be the exponent.
Like you don't even know what you're saying. But you're still trying.
That's Tesla to take the derivative of this, you have to use this derivative again. So you just have to, that's the derivative of the outer function. Then you need to multiply the derivative of the outer.
Which part?
So I just made this probably okay.
No. So like this would be the derivative of this is equal to power times the derivative of that. So you have
So
this.
cosine of this.
But it's just this power times the derivative
Instead
of.
of fly. And then stuff is like, no, it's not safe for girls to drink. So, I was like, I don't need a man to protect me.
I do or a solid to my first class out here.
It's fine.
By myself too, with dogs.
I was raised in Detroit, like, I'll be fine.
Yeah, just to
I was a great candy. So, like, the one I got
It's too hot there.
Yeah, I was unsure as to which path I was taking.
On the inside?
You leave that alone.
No, you didn't. No way.
Yeah.
It's negative sign, it's times the sinus.
No, negative sign
Yeah.
or negative sign of e to the sin x times e to the sin x times cosine x.
Oh, I did it right. I just didn't put cosine, I just put derivative of sine.
Yes, exactly.
But wouldn't it go to negative? Because it's the opposite?
Cosine's not negative. So like,
Except
it's only
for
the sin
the
x is
derivative of
negative.
e to the
I thought it was like if one was positive, the other was negative.
So the derivative of cosine is negative sin x, and the derivative of cosine is cosine.
Right.
Okay,
So even though.
here's what I did.
So
I
for
did
the
the
first
whole
part,
like,
you just do the derivative of this.
Yeah.
Yeah. That might
you
you pull
replace the
this
x.
out, you still have to do the derivative of that.
the outside
out,
function
Yeah.
And then you
is
still multiply it by.
The same thing, yeah.
Okay.
I'm just saying like u,
Thank you.
right? And that's what u is. So u equals u to this. And so you find u prime.
This is wrong, right?
So here, you take the derivative of that sine. But you're supposed to leave that one, so that should be a negative sign of x times that. Just should be negative sign of this one.
Oh, I see.
Yeah.
This is the x.
Yeah. Still multiply by the derivative of this.
Actually, to get more of this homework done and stop
So
this
the rest of
chemistry.
okay.
But this right here shouldn't be here. It's just here.
Putting the x's up there.
Wait, this would be just where the x was.
Exactly. Yeah.
Okay,
Yeah.
okay, that makes sense.
You know, we did that
So you're using two.
Yeah.
So you do
I
derivative.
didn't need it all done. I just did an exam review. So there's like, just doing the homework and stressing about
So I
that.
guess to
After
derivative.
x minus that's either two w.
This.
It's minus w. So it's just, that just turns into e to the w. Or sorry, two e to the w.
Oh, okay,
March
gotcha.
start, I get full credit.
Yeah.
So trying to find out spiders get it done. What's the-
I don't like what Alex like last time, I'm just stressed.
Of what?
Getting all my homework
Oh,
done.
dude, that's terrible.
Finals week, you know.
Apparently I'm on a strong test.
Yeah. Yeah, I know I'm strong.
Now let's do.
Alright, let me see your answers. Okay, so it's negative sign to e to the sign.
As long as you know those are multiplied, right?
Yes.
This, not minus this.
Right now I'm declared, but I'm getting associate science and then I just I do have this over there for this one.
You know what you're gonna do with it?
That's what I have. Yeah, I'm gonna go and get something.
So no longer.
I'm sorry. What about you?
The one that's not crossed out.
Sometimes I don't know better.
This the base up. I get it, don't worry.
Oh, you have it.
Oh, I get what the question
Yeah.
Here's the This is the same, but this is the
You guys
But I just need to actually complete it and then and I'm saying if you don't actually understand it. Yeah, I have it. I've taken it in high school. I've been trying to test out of the intro.
trying.
But I can study for it.
I literally got psychologist on Tuesday yesterday. She was like, how are you doing in school? You know, I don't even care about my grades anymore because I'm literally trying my best. There's not anything else I can do.
Okay, so it's the cosine of the e to the sine x. If you're using version 1, u is e to the sine x, and then that makes y cosine of u. Okay. So don't put an extra x in there with the cosine because it's the cosine of that function e to the sine x. So the derivative, we take the derivative of just the outside piece and leave the inside piece alone. So the argument is left alone as e to the sine x. And then we take the derivative of the outer piece, which is cosine. Derivative of cosine gives us negative sine. So it's the negative sine of e to the sine x. Okay. So there's the derivative of the outer with the inner function left alone. And then we have to multiply all of this by the derivative of the inner. So just like with the product rule and the quotient rule, they involved extra derivatives, especially within the chain rule. I think it's important when you're just getting the handle of this to write that out, just like I've written it out. So we know that, okay, well, when I take the derivative of e to the sine x, then again, I have another chain rule inside of that. So off to the side, I'm going to compute the derivative of e to the sine x. We just spent a lot of time talking about this. It's e to that power times the derivative of the power. Okay, so that gives us e to the power of sine, all of that times cosine. Okay, so then that's secondary to what we're doing here. We need to take that derivative and put it in for this derivative. It's cosine times e to the sine. Times the negative sine part. Okay, and that's our derivative.
Does it order matter?
The order doesn't matter. We just have to know that the negative sign of e to the sine x is one factor, cosine's another factor, and then e to the sine x is your third factor. It doesn't matter, you know, could put the negative cosine of x first, but it's important to know that the sine of e to the sine x is one thing. So that's our negative sine of u part, right? If we were thinking about version 1. So that's one thing in and of itself. Did anyone have any questions or issues with that?
Could you do it all in the same area and like make a U2 for like 3 seconds?
Yeah.
Okay.
Yeah, so really if you're using version 1, this would be sufficient to take this derivative, but then when we have the derivative of e to the sine x here, using version 1, you can make another substitution. You might say v is equal to sine x, that function is e to the v, right? So I think version 1 is a lot easier if it makes sense to you. Because then we can just take all of these subsequent derivatives and compute them off to the side and put them back in. I'm going to forego this example and use one from your homework instead. Okay, that'll work. I'm going to get this problem from your homework. It's the tangent of 6x e to the x. And maybe we can look at another one. Focus on. Okay, so this, we want to find y prime. So really now, what we're looking at here is what rule would be involved in taking that derivative.
Chain.
A what? A chain rule? Not a power. Did you say power?
Yeah.
Okay. Yeah, so you really should see two things, right? We see a function composed with another, and the inner function is also a product. So really there's two rules that need to be applied here. But we look at what is the overall structure of the function. It's the tangent of something, right? So the overall structure of y is a composition. So to take its derivative, we're going to use the derivative rule for compositions, which is the chain rule. Okay, any other derivative or derivative rules that show up as a result of that, then we can look at those off to the side and compute them separately. So y prime, we take the derivative of the outside function and leave the 6x e to the x alone. So what's the derivative of tangent? Secant squared. So it's the secant squared of 6x times e to the x. Okay, so there's the derivative of the outside, leaving the inside alone, multiplied by the derivative of the inside. Okay, and that's all the chain rule tells us to do. So there's the chain rule. Unfortunately, another derivative showed up, so I'm going to compute that derivative off to the side. But is everybody okay with just that initial derivative based off of the chain rule? Any questions? Okay, so then here we're going to find separately the derivative of 6x e to the x, like it's a different, entirely new function. So the derivative of 6x e to the x, now we can start thinking about the product rule. It's a product of two functions of x. You can take the derivative of it as is, where the first is 6x and the second is e to the x. Or since the 6 times the x times the e to the x is a constant, we can also take that out if you wanted to. Doesn't matter. One version will have the 6 distributed in all terms already. The second version will just have the 6 factored out, but it's all the same. So we take the first times the derivative of the second plus the second times the derivative of the first. Okay, so that gives us 6x times e to the x plus 6 times e to the x. If we did this version of it where we factored the constant out first, we would have 6 times x e to the x plus e to the x. You can see they're exactly the same. One's just factored a little bit, I guess. So that is the derivative of the inner function here. We're going to take this and put it back in place of our derivatives above. Do y'all have any questions on that one? Here, what we've done? Okay, so we're going to just take 6x e to the x. In place of this whole thing right here. Just be mindful that both of those terms are multiplied by the secant squared of 6x e to the x. So that's good enough for the derivative. No to go any further. If we're just taking the derivative, that's fine. Do y'all have any questions on that?
So my math will be taken out.
Should, yeah. All right. Any questions on 3.7 then? It's kind of hard until, we've seen a couple of examples, but until you start doing it, you don't know what you don't know, right? So it's important to keep up with the homework and things so we can address any issues that you have, as we move along, as opposed to at the very end of everything. So there's quite a few homework problems. They're going to look all probably mostly different than the ones we did in class. But that's why you have to practice these, because especially with the chain rule stuff, I think it's less clear cut than when you have like a product or a quotient. Okay. Well, if any issues arise during the homework, then please let me know. You can always email me if you don't want to ask in front of class. So if you have any issues with that, just let me know beforehand. Send me an email or something and we'll talk about it. So let's take a break before we start something new. All right, section 3.8, technique of implicit differentiation. You can think of how we've been taking the derivative up to this point as explicit differentiation, where we're given a function explicitly as y equals to, like x squared plus 2x plus 1. So we've explicitly known what the function was in terms of x. Here in 3.8, we're going to look at what happens if we're unable to solve for y, so I can express something as y equals to. A lot of times you can't do that with a particular function. So here's an example. Implicit differentiation was y equals to some function of x. If you have x squared plus y squared equals to 1, then in a function like that, if you didn't know how to do implicit differentiation with a function like number 1, you could just solve for y. And you say, okay, well now I have y in terms of x, and I can take the derivative of both of those functions. Right? So you would just have 1 minus x squared, or the 1/2 chain rule would be used. So we could find that. However, a function like example 2, there's no way you could solve for y. So there are some functions written implicitly that we cannot explicitly solve for. Okay, so functions like that, we need a different method to find the derivative, which is the implicit differentiation. We're still operating under the assumption that y is some function of x, in example 2, we just don't know what it is because we can't express it as, plus or minus square root of 1 minus x squared, right? So here we can explicitly see what y is as a function of x. In example 2, we can't see that. But y is still the dependent variable. So y is still a function of x, even though we can't represent it that way. So the techniques of implicit differentiation does involve the chain rule, which is why we have to talk about the chain rule first. So, find the derivative of x squared plus y squared equals to 1. We'll find that explicitly. Oops. So we'll, just like in that previous page, we first solve for y. And come up with the fact that y is the positive and the negative square root of 1 minus x squared. By the way, the relation x squared plus y squared equals 1, what is that?
Circle.
It's a circle with a center of
Origin, 0, 0.
at the origin and a radius of 1. So does it make sense that we have two functions of y? Algebraically, yeah, we've solved for a square, you get a plus and a minus. But in thinking about what the derivative would actually describe for us in terms of our circle, so if we have our function here, circle radius of 1, and we look at the derivative at any point on this circle, the derivative should tell us what's the slope of that circle. Like if I said, for instance, well, what's the derivative at this point? Then my derivative should measure that slope. Or if I said, what's the derivative at this point? My derivative should measure that slope. Well, why do we have two? Why are we going to have two different derivatives?
Because at some points the slope is going to be negative.
Right, because at some points on the circle, let's say this one, at some points the tangent line or the derivative is positive, right, because we have a positive slope. And at other points, the derivative is negative because we have negative slopes. So we have two functions of y, plus or minus root, which is going to give us two different derivatives. So when I write both of these functions of y out, y is the positive root of 1 minus x squared, and y is the negative root of 1 minus x squared. That's going to give me two different derivatives. When I talk about y equals the root 1 minus x squared, what part of the circle does that give me?
The first and third quadrant?
Yeah, the top half of the circle, because y is positive. So this function here actually just represents the top half of that circle. This function is where the y values are all negative. So that function gives me the bottom half of the circle. When we put those two functions together, we get a circle, which isn't a function, right? We can look at the circle as two individual pieces that are functions in their own right. Okay. So we can find the derivative now of y explicitly because we explicitly know what y is. So the derivative of y here, we take the derivative of the outside and leave the inside alone. And then we multiply that by the derivative of the inside. So that's our chain rule. We have 1/2 times 1 minus x squared to the negative 1/2 times the derivative of 1 minus x squared, which is minus 2x. So the negative 2 rather than the 1/2 divide away. We have this x times the quantity 1 minus x squared to the negative 1/2. Or if we want to write it as negative x over the square root of 1 minus x squared. We can do that. So that is explicitly our derivative for the top half of the circle, right? This function, negative x over root 1 minus x squared, that function gives us the slope of the tangent line at all points that are on the top half of the circle. So let's write this here, the slope of the tangent line at all points on the top half of the circle. Which would make sense on the top half of the circle, or does it make sense? On the top half of the circle, notice our derivative is negative x over the square root. We know that the root is always positive, no matter what it is. But then we have the negative x. Why the negative x? If I'm over here, let's say at this point, what's that slope?
Positive.
We've got a positive slope, but this is a negative x value, right? So if I take that negative x value and plug it into my derivative, then I also multiply that negative x value by a positive, and all of this turns out to be positive. If I'm over in the first quadrant, all of these things have a negative slope, but we have a positive input into the derivative, positive x. That's negative of that number, so we've got a negative slope here coming out. So I mean, at least we can look at the figure and say, well, yeah, that does make sense based off of where the inputs are. If they're negative, we've got positive slopes. If they're positive, we have negative slopes, and that's what the derivative confers. Okay. So how about the derivative for the bottom half of the circle? What would that be?
Positive x over
Yeah.
root 1 minus x squared.
So we saw the only difference in those functions was one was positive, the other one was negative. In other words, when we take the derivative of the negative square root, that negative 1 can come out of the derivative and multiply in later. So here's our derivative, we multiply it by negative 1, and we get this derivative. So that derivative is the slope of the tangent line at all points on the bottom half of the circle. The reason we're doing this is because we're also going to look at this and then take the x squared plus y squared plus equals 1 and take the derivative implicitly, and then we'll see if the derivatives match from method to method.
I think I might have messed up. Isn't it x squared minus 1 on the bottom for the second?
No, it's because it's the same.
Oh.
Right, the only difference here is this y is equal to negative 1 times this square root. And we've already found the derivative of this square root part, so all we have to do is multiply that derivative by negative 1. So we found the derivative of the square root part here, and all we've got to do is multiply this by negative 1 to get that derivative. So that's explicitly, we found the derivative. Now, going back to the original relationship, going back to the original relationship, we can look at finding the derivative implicitly. And implicit differentiation does not require us to solve for y first and then take the derivative like we did explicitly. So with implicit differentiation, the general assumption is that the functions that are given to us, we can't solve for y. So we're not going to waste our time. We're using this example because we can actually do both and see that it actually gives us the same derivative. But in general, we don't have to solve for y to take the derivative. We do still, though, however, have to remember that y is a function of x. Whether we can solve for y or not, y still depends on x. So when we take the derivative of this implicitly, it might help to think that we're taking the derivative of x squared plus y squared. And y squared is some, we're going to pretend it's some unknown function of x. We literally just saw what y was because we solved for it. But in the instances where we can't solve for y, we have no clue what that function of x is. So we leave it as y or f of x. Is everybody okay with that? That's like the primary thing that we're dealing with implicit differentiation. Okay. And so we just take the derivative of the equation. Either one of these, take the derivative of both sides of the equation. So I'll just put that step here. You don't necessarily have to write this out, but just so we're clear, there's the expression. Now we're going to take the derivative. What is the derivative of x squared? 2x. Plus, what's the derivative of 1?
0.
0. What's the derivative of y squared? 2y. What do y'all think? Y is a function of x. So look at it this way. If I had some function of x squared, I have to use the chain rule to take that derivative, right? The chain rule says to take the derivative, I take the derivative of the outside, leave the inside alone, then do what? Multiply by the derivative of the inside. Right, if that were like, x squared minus 1 squared, or 3x plus 5 to the 100th, you wouldn't just say that the derivative is 100 times that quantity to the 99th power. So what are we missing here? The derivative of y squared is not 2y. What are we missing? The y prime. Yeah, we're missing this derivative piece. We're missing the derivative of y. So it's 2y times y prime. So that's really the technical reason behind that. I think it's easier, like operationally, to think about when I take the derivative of y, I apply all of the normal rules that I normally would, but the only additional step is that I've got to multiply all of it by a y prime. That's in practice what it boils down to. So if I say take the derivative of the sine of y implicitly, so the derivative with respect to x, assuming y is a function of x, we would take the derivative of this as we normally would. So normally we would just say it's cosine y, right? But y is a function of x, so we also need to multiply that by the derivative of y. That's really all implicit differentiation boils down to. It's a very simplistic way to look at what we're actually doing, though. Y represents an unknown function of x. So we have 2x plus 2y y prime equals to 0. Did we find the derivative? No, the derivative is y prime. So now we have to solve this equation for y prime. We're going to divide the equation by 2. So we have x plus y prime equals to 0. We have y prime equals to our negative 2x. Add that to both sides. And then solving for y prime, we just divide by y. Y prime is negative. Sorry, that 2 was gone. My bad. We have a negative x divided by y. And so the difference here, we see that the derivative depends on both x and y. Most of the time, implicit differentiation does give you a derivative in terms of both x and y, because the reason for that is just pretend we couldn't solve for y. We don't know how to express y as a function of x. And this example we're using is just so that we can move back and forth between the two operations or the concepts and see that they in fact are the same. When we did this explicitly, what did we say y was equal to? That was y. I think maybe we were thinking of y prime. So we just so happen to know what y is here. Most of the time you won't. Explicitly, our y was this. Does that match with what we have as our derivative? Negative x over the root 1 minus x squared and x over the square root of 1 minus x squared. Does this result negative x over y match with that? Yeah, because y is the positive and the negative square root of this radical here, right? So if we write this as what we know y to be, and this is negative x on top, right? Negative x over the positive root, that's here. Negative x over the negative root, that's here. So it's the exact same derivative, it's just expressed differently. Here, implicitly expressed as x and y, because we're pretending we don't know what y is, but in fact we can verify that it is indeed the same result. Okay. Do y'all have any questions on this?
Do you have to do explicit and implicit?
No.
To find the answer?
We did both ways to show that they do match. We're going to just focus on implicit differentiation here in this section. So you don't have to do both,
Okay.
right? Because they both give us the same result.
So are you given the y?
Yeah, you're given the relationship between so you're given x cubed plus y to the third equals to 12 or whatever. So you're actually given the relationship. Oops. And this circle here is just to remind you that when we come up with the implicit derivative y prime is negative x over y as the slope of the tangent line on the unit circle. Hopefully it's clear that this derivative is not defined or does not exist when y is equal to 0. So the two locations on the unit circle where y is 0 are which ones?
Or crosses the x-axis.
Yeah, the x-intercepts. So the derivative is not defined here, and the derivative is not defined here. Why is the derivative not defined here? Other than the fact that we see what the derivative is, slope of the tangent line-wise, what happens on the unit circle at those 2 points?
It's completely vertical.
Yeah, you've got a vertical tangent line. So here, visually, that's why we're saying that the functions, or the derivative rather, is undefined there. So those are our vertical tangents. What happens when x is 0?
Slope is just 0.
And our derivative, right, if y can't be 0, 0 over any y value is going to always be 0. So when x is 0, that gives us these 2 points. When x is 0, we have that point and that point. When x is 0, y prime is 0. We have the slope of our tangent line is 0, or we've got a horizontal tangent line there and there. So just to further convince ourselves that this derivative does actually make sense, we can look at those places where the derivative is undefined, vertical tangents, and where the derivative is 0 gives us those horizontal tangents. Okay. Do y'all have any questions at this point? It's a very different way to look at things. Every function that we've seen up to this point, even in previous courses, has always been explicitly defined. Okay, so find the derivative of x squared plus xy minus y cubed equals 7. And then here's what this actually looks like. So most of these things do not actually represent a function, because the idea is if I solved for y, if I could solve for y in this relationship here, how many different functions would I get?
However many y's you have.
Yeah, however many y's we have, and we have 3 of them, right? We basically the highest degree here, we would have 3 different functions of x if we did solve for y. So I don't know exactly what it looks like because I haven't plotted it, but maybe from here to here is one function of x. This is another function of x. And then this is, this is another function of x. That's really what we would be looking at if we could solve for y. But that's super tedious to solve for a cubic. So we're just going to take the derivative of the equation. So the derivative of x squared is 2x. Let's just write this here, plus the derivative of xy. Like this, derivative of xy, minus the derivative of y cubed. Equals to the derivative of 7, which is 0. So what would the derivative of the y cubed portion be? 3y squared times y prime, right? Don't forget, when we take the derivative there, just tack on a y prime. So that's 3y squared times y prime. How do we take the derivative of x times y? You have to do a product rule, right? It's a product of 2 functions of x. So So let me just give us some space here and find those derivatives individually. So the derivative of y cubed is 3 times y squared times y prime. Now, if you need to think about it as I'm actually taking the derivative of y to the third power, but y is some unknown function of x. If you have to write it out like that to remind yourself to include the y prime, there's nothing wrong with doing that. So that's 3 times f of x squared times the derivative of f of x via the chain rule. And since we don't know what f is, the best we can do is notate its derivative as f prime. This right here, all we can do to take its derivative is just call that f prime. F prime and y prime are the same thing. This is 3 times f of x squared. Again, we might as well just call f of x y because we know it's some function of x. So it's 3y squared f prime or 3y squared y prime. Does everybody see that? I don't know if that's a helpful way to think about it, but that's, in actuality, that's what we're doing. So 3y squared y prime. About the derivative of xy, we have a product. And I don't know if it's helpful to think about this way, but it is x times f of x. That's what we're taking the derivative of here. So we have the first times the derivative of the second. What's the derivative of y? Y prime first times the derivative of the second plus the second times the derivative of x. What's the derivative of x? 1, right. Or we say first times the derivative of the second plus the second times the derivative of the first. Okay, so x y prime plus y is that derivative. Do y'all have any questions on that? So those two need to go into our workup here. So the derivative function or equation is 2x plus x y prime plus y minus 3y squared times y prime equals to 0. Okay, so there's two things we can do from this point. In the direction you go depends on the instructions of the problem. So the instructions of the problem could just say find the derivative, at which point we would need to solve for y prime. So let's just write those out. One, the instructions could say find the derivative. In which case, solve for y prime. The other thing that it could say is find the equation of the tangent line at a given point. So we'll just condense that derivative at a point. Honestly, finding the derivative at a point I think is easier, because if all you're asked to do is find the derivative at a point, we just take the point xy plug in. When we do that, it's going to give us a bunch of numbers times plus or minus or times y prime. So when we're able to plug in explicit numbers like 2 and 4 for the x's and the y's, then that just leaves the unknown as y prime. If we have to solve for y prime, then we're always going to have the x's and y's also floating around that. So we're going to look at both of these just so we can get a sense of in either case, if they say find the derivative or the derivative at a point, in either case you can solve for y prime and then plug in. I personally think it's easier to take the derivative as we have it here, and if we've got to plug in a point, plug that in just how we have it and solve for y prime.
Just a question on the equation that you just squared.
Mhm.
The second y, it should be a y prime to the right.
This one?
Yeah.
No, because that was first derivative of y plus y times the derivative of x.
Okay.
There's our sort of secondary work for that one. Let's just say that they ask 1, now find the derivative. So usually it involves, you've got to take the derivative of the equation and solving for y prime. That's typically the steps involved when you apply the technique of implicit differentiation. And let's see. Okay, we'll use 3. So if we're just finding the derivative, that means we have to solve for y prime. So we have 2 terms, xy prime and 3y squared y prime, that involve the variable, the thing we're solving for. So we're going to leave those 2 on one side of the equation, and then we're going to put everything else, meaning the 2x and the y, on the other side of the equation. That way we can factor out what we're trying to solve for. So then we factor out our y prime. And then we know what to divide by. So y prime is negative 2x minus y all over x minus 3y squared. Okay, so that's the actual derivative of that funny looking curve. And that's always the process to solve for the derivative. You keep the factors that have the prime or the derivative on one side together and put everything else on the other side of the equation, factor out the y prime, and divide by what's left over. Okay. So that's what we're after if the problem just had us finding the derivative. Do y'all have any questions about that? Yeah.
Just going back to the derivative of xy, why do you not have like an x prime, I guess?
Well, x prime here, remember we're taking the derivative with respect to x. So
Okay,
x prime would just be 1.
Okay, that makes
Yeah.
sense.
Yeah, y is the unknown f of x.
Okay.
So that's when we have to add the prime to it because of the chain rule. So let me just write that here, just so we're not confused. Times the derivative of x, which is 1. Yeah, are there any other questions? It's really important that we are all on the same page. Oops. Okay. So after taking the derivative of the equation, depending on what the instruction said, that one said find the derivative, maybe a different set of instructions says, find the derivative at the point three, two. Really, when you're asked to find the derivative at a point with something like this, you've got two options. You can solve for y prime, then plug in x and y, or we could plug in x and y first and then solve for y prime. I think it's easier to plug in x, y first if we have an actual x and y. This is our x, this is our y. We're going to plug that into the equation. It's 2 times x plus x times y prime plus y minus 3 times y squared times y prime equals to 0. So now when we plug in our points immediately before solving for y prime, then we just have numbers and y primes. We don't have y primes, x's, and y's. So I don't know, it might make things a little bit easier. So we have 6 plus 3y prime plus 2. We have minus 12y prime for this one equals to 0. Then we just combine like terms. You've got a 6 and a 2. That gives us 8. You've got a 3y prime minus 12y prime. You have minus 9y prime. And that's equal to 0. So with an equation like that, I think it's a little bit easier to solve for y prime, right? Once we plug in a known x and y. The solving for y prime here, easier than solving for y prime above, I think. So on that funny curve that we had in the beginning, at the point 3, 2, the slope of the tangent line is positive 8/9, is what that tells us. If you want to verify, since we already did find y prime, if I plug in x equals 3 and y equals 2 here, you should verify that for yourself that you do come out with 8/9.
What's a negative number if you put it in there? Because it would be like 2 squared, but
Yeah, you subtract 8 and divide by -9, so that's negative.
Yeah, so this would be negative 8 over negative 9. So, find the derivative at a point however you want to do that. Either by finding y prime first, or by plugging in first and then finding y prime. Is everyone clear on that? Does that make sense? Either way, it doesn't matter.
For the first question that you had, if we end up with 2 y primes, we've definitely done something wrong, right?
Yeah, like in the same, for the same term?
Yeah.
Yeah. If you end up with 2 y primes, like y prime times y prime, then you've probably done something wrong. Yeah, I think that's a safe rule to follow. Let me go back up to our graph and just show that. Here. So here's, let's see, 5, 1, 2. So what we just did, there's the 0.32 on that curve, and we found the tangent line. Here does have a slope of 8/9. So then with the slope of the tangent line and the point, it would be easy to write out the equation of that tangent line at that point. But, you know, it's kind of beside the point right now. Are there any other questions on that example? So here's the relationship, and we want to find the equation of the tangent line at this point, 1, 1. So two things we need for the equation of the tangent line. We need a point, which we have, and we need the slope of the tangent line, the derivative, at that point. So let's take a second and I'll figure out what the derivative of this function is, or this relationship, rather. Hopefully the x and the constant are easy. What's the derivative of y to the 2/3?
2/3 y to the negative 1/3 times y prime.
It's y prime. So let's, you'll agree with that? It's 2/3 y to the negative 1/3 times y prime. So we just take the derivative normally and then multiply it by y prime. Right. That's really all we're doing. Okay. Does anyone have any questions about that? So from here, there's two things we can do. We can either take what we have and solve for y prime, and then plug the x and the y in, or we can just straight away plug the x and the y in and solve for y prime. So which one do y'all want to do? Plug in xy first, or find the derivative first? Find the derivative first. That's what I heard. So let's find the derivative. Let's just multiply everything by 3/2 so we can get rid of the fraction. So we have x to the negative 1/3 plus y to the negative 1/3 times y prime equals to 0. Solving for y prime, we have to subtract the x to the negative 1/3 on both sides. I'll just write it like this. So we're going to subtract that on both sides. That's y to the negative 1/3 times y prime. And we'll divide through by y to the negative 1/3. Does that look all right? Just algebraically. We can take care of those negative exponents. We could write this as negative of y to the positive 1/3 over x to the 1/3. So that is our derivative. This is y prime. Don't forget that negative. Okay, so there's the derivative at any point on this weird diamond thing. We want the slope of the tangent line or the derivative at 1, 1. The negative of 1 to the 1/3 over 1 to the 1/3. It gives us what?
Or -1.
Yeah, -1. That. So what is the equation of the tangent line at 1, 1? We've got everything we need. We've got the point, and the slope of the tangent line is -1. Y minus 1 equals to our slope, -1, times x minus 1. Or we have y equals to -x, we have +1, +2. So there's the equation of the tangent line. Any questions on our process here? Okay, so there's a point where our tangent line was -x plus 2. See, that's tangent to that point. Do y'all have any questions? So a note about when you have to find the second derivative implicitly. When you find the second derivative, keep in mind that we also have a relationship between x and y that's given to us originally, and what the y prime is. So when you find higher order derivatives implicitly, you always go back to the derivative and the relationship given to see if that can help you simplify the higher order derivatives. So we already know that, or we've already shown anyways, that the derivative is -x over y. So then we find the second derivative by taking the derivative of negative x over y. So this is what we're doing. I guess there's a couple of ways to think about this derivative, negative x over y. We would use the quotient rule, or we could write this as the derivative of negative x times y to the negative 1, and then we could use a product rule. Either way, a chain rule has to be used to take the derivative of y. So which one of these do you want to take the derivative of, the quotient or the product? They're both the same.
Quotient.
Okay. We're going to use this one. At the bottom, y times the derivative of the top. The derivative of negative x is negative 1. Bottom derivative of the top minus the top times the derivative of the bottom. Derivative of y is just y prime. All over the bottom squared. So there's second derivative, but we do have a way to simplify this because that y prime sitting there, we know what that is, right? We know that y prime is negative x over y. So we're going to use that relationship to write this as negative y plus x times negative x over y, that's y prime, all over y squared. The idea is when we write out second derivatives explicitly, there's not other derivatives that show up. So the idea here, when we write out the second derivative implicitly, we don't want other derivatives showing up in that either. Okay. So I mean, that seems okay as it is. We don't have any derivatives showing up, but we can simplify this. Okay. It actually simplifies really nicely. So we've got some sort of mixed fraction, looks weird. From this point, what we're going to do is multiply by y over y. So we'll continue this on Thursday.